In the earlier video, we have already examined how the EMF is being produced when the coil is being rotated in a singular direction. So in this video, we will turn this information into a graph. So we'll be using worksheet 22.3. So if you recall, what we have found out in the earlier video is that when the coil begin at 0°, meaning that the coil is flat, actually you will have a max EMF. And when the coil is at a vertical plane, so for example, this is what I mean by horizontal, when the coil continue to rotate and it reaches a vertical plane, you will find that the EMF becomes 0. And we have also learned that once it rotates slightly past the vertical plane, the EMF is going to reverse, right? It's going to reverse its direction. And of course, it will go back to a maximum when the coil go back to its horizontal position, which is 180°. You will get back a max EMF, and the cycle basically repeat. When it goes back to 270, it is going to be 0 EMF again, right? So that's what we learned. So I'm just going to dot this so that you can see how it changes, right? So we are going to put this on a graph. So here you can see that at 0, I'm going to get a maximum. At 90, I'm going to get 0. At 180, I'm going to get a maximum. But in this case, because the EMF is being reversed, my maximum will be a negative maximum. And then the cycle basically repeat. So actually, if you work out the math, it is actually similar to a cosine graph. You do not need to know how the curve is actually being calculated because you have not learned what is magnetic flux. So I cannot show you the math as well because it won't make sense to you. So what you need to know is that this is basically how the amount of EMF will vary as the coil rotate in one complete rotation, right? You should also read up the textbook and refer to the SLS. You will know that actually the faster you spin the coil, the more EMF you get because of conservation of energy, right? The faster you spin, that's the higher work done on the coil, then obviously you are going to get a higher output in terms of electrical energy. So we are going to use the next few example to illustrate to you how would the graph of EMF output versus angle of deflection changes as I give new condition to the context. So for example, here I have the stem of the question, which tells you that I have a certain EMF output as the angle of deflection is changing. So they didn't give you 0°, 90°, and so on and so forth. You need to be able to deal with this. So most likely you should know that this definitely will give you one rotation. So here you can already see that this graph involves 3 complete rotation of the AC generator coil, right? Then here it says that, oh, okay, can you sketch a new output if a certain new condition is added to it? So here it says that, oh, you have a second coil. So what do I mean by a second coil? So initially I have something like that, right? I have a singular coil that is trapped between two magnet, right? So what if there is a second coil being added? So for example, if now I go and add in a second coil, right? So maybe this particular line that you are seeing corresponds to the green coil. So this blue line that you are seeing corresponds to the induced EMF produced by the green coil. So now they are asking you, what if now I add this black color coil? Can you add the induced EMF that is being produced by this black color coil, this new coil, onto the same graph? So here you can see that and this new coil that you have added is 90 degree away from the original coil. So what do they mean by 90 degree? It refers to this. So this is what they call by 90 degree from the original coil, right? This is the 90 degree. Well, so what to do? Well, it's quite straightforward. So you can see that the green coil actually produced 0 EMF at the beginning. So meaning that at the beginning, the green coil is actually at a vertical position. That's why it is producing 0 EMF. And this means that my new coil, the second coil that is 90 degree away from it, must look like this, right? So if my new coil is horizontal, it means that my new coil must have a maximum EMF. So if I keep on doing this, I will be able to see that the new EMF that is being produced will be, for example, when my green coil is at maximum, my new coil will be at 0, and when my old coil is at 0, my new coil is going to be at negative maximum. So if I keep on doing this, basically I will have a graph that is 90 degree off. So oops, very hard to draw. So I think better to have some guiding dots. If not, very easy to get penalized. Right, then now it's easier. So now I can draw it. This is too straight. So I need to give it a bit of curve. Yeah, no need to be a perfectionist because it is a sketch. So as long as you don't show sharp corners, you should be fine. Right, so I got it. Okay, the next question. Now I have another condition. The speed of rotation is reduced by half. So when the speed of rotation is reduced by half, the first thing that should come to your mind is that, okay, so now I have less work done on the thing, right? And therefore my amplitude of my output EMF should be half, right? So the first effect I can think of is that my induced EMF is going to drop in terms of the amplitude, right? But because it is being rotated at a slower speed, it means that the frequency of it coming out will also be lowered, right? Because now it is spinning slowly. So meaning that the time taken for one complete oscillation will be lowered. So it means that the frequency of my EMF alternating will be lower. The frequency will be lower, right? So the other effect of rotating it slower is that now we know that the time taken to complete one rotation of the coil will now be longer. And so the implication is that the frequency at which the direction of EMF reversing will be lower, right? But in this particular graph, because the x-axis doesn't rotate time, it rotates the angle of deflection, you will find that this particular effect will not be reflected on this graph. Right, but if you have a graph that is against time, right? So at the very beginning, if this is the EMF you get for this amount of time, so for example, you get this 1 1/4 a rotation in, let's say, 4 seconds, if now you are rotating it slower, then obviously you are going to get a smaller you will take a longer time to complete one rotation, so the frequency of the wave will be different, right? So here on this graph, you will only see the effect of this guy, right? So therefore you will have something like, so this 1 2 3, so maybe here, here, here. I'm just roughly dotting the thing so that I can use it as a guide for me to draw my curve, right? It doesn't look very nice, so let me try again for a smoother graph. So this kind of thing, if you didn't practice in your daily homework, you won't be able to do it quickly in your exam. So try your best to practice when doing your A math or physics. So there you go. Yeah. So here you get the last part. Now you have a generator that is connected to a diode. So what does a diode do? Basically, if you have a AC source like that connected to a diode, when you have an AC source, basically what it does, so I will draw two identical circuit to illustrate to you. So at one instance, the current may go in this way, and because the diode is in this particular direction, the current will be able to go through. But when the direction of the current alternates and become anti-clockwise, you will find that this thing will become like an open circuit and it will not let the current flow through. Yeah, so that is how a diode works. So because of that, if you have a diode connected to the generator, you are going to get the positive, but when it goes into the negative, when the EMF or the direction of the current reverse, you're going to get a flat line and then go back to here, the diode acting like just a normal wire. But once it goes into the reverse, it will block it and there will be no EMF, and then like that. So that's how a diode will affect the graph of EMF versus direction of reflect.